Welcome to the third video where we will be doing various simulations of LTSpice that you will need in electronics. So there is 4 simulations, or the fourth actually being a function that we will be looking at: transient simulations, AC analysis, DC sweep, and the FFT function. So the transient simulation is time-based. AC analysis is for our frequency responses. DC sweeps is for input versus output. And FFT is to see harmonics in our system. So first up, our transient simulation. So it's either voltage or current versus time. So it's time-based simulations. This simulation is also used to find our DC bias points, and it can show us different signals at different nodes in the simulation. So let's jump into that. So for the transient analysis, I set up a BJT amplifier using a split emitter configuration using a BC547 transistor, and I designed this to have a gain of exactly 10. I added the source and a source impedance of only 1 ohm, so I can have a resistor here and then just play around with this resistor value right here, and 100 meg on the output, so that we only see the gain of this amplifier itself. Okay, here I used some of the tags that I mentioned earlier, or the nodes that you can label, and I set up the power supply to be a dual power supply. This is how you set up a dual power supply in Spice, and you can put this anywhere in your schematic and put it away from the rest of the things, and it's not so cluttered then. So these nodes VCC are connected and that VEE is connected. So let's do a basic transient analysis. So in the lab you will be hooking up a oscilloscope to this thing to do your measurements. Okay, so need to do that. We first need to set up the source. So advanced sine wave. Let's give it the amplitude of 10 millivolts. And let's run it at 1 kilohertz. Boom, done. Okay, running the simulation. So if you want to run transient, we hit the running man. The first one that's always open is the transient. So you should specify the length of a simulation. And I'm going to go and say 100 milliseconds. Then you can specify the time to start saving data. And this is, you always want to skip the initials of your simulation, because there's capacitors, they have some charging time, and some of your DC points will be floating, and you don't want to see that. So you want to start recording data after a while. Let's go 90 milliseconds. So we are only going to see 10 milliseconds of data in our plot. Okay. Then there's a couple of options here. We're not going to bother with them in this simulation. The only one that might interest you is to start external DC supply voltages at 0 volt. This is when you're doing oscillator simulations, and you need to basically force the supplies from 0 so that there is an imbalance in your circuit, so it will start oscillating. Okay, stop simulating if a steady state is detected. So if you're only doing a DC analysis and you want to find a point where everything stabilizes in your circuit, you can just tick this box and your simulation will end the moment that you reach a steady state. Okay, right, no need to worry about the rest. We click OK here. It will open up a window where we can see our transient. So the simulation has already run. So if we double click this point here, see there is a oscilloscope probe, and we set our sine wave to 10 millivolts. This is the input that we have, and after a 1 ohm source, it's not much of a difference in any case. Okay, so we click here on our output. If you double click, it takes away the previous simulation. If you single click, they just add on to one another. So double clicking, we can see that we have a gain of exactly 10 with this. Okay, so there is our input, there is our output, and they are also 180 degrees out of phase with one another. Also note, only 10 milliseconds of data was recorded. Right, that is a basic transient analysis. Let's quickly change this and let's start saving data from 0. Click OK and run. In some simulations, it doesn't really matter the startup time because the capacitors load so quickly that it makes no difference. But be cautious, in some simulations it does happen. So that is why I always include this little bit of a buffer. Right. So that is AC simulation. So this is after a capacitor, so there is no DC. So this is a DC blocking capacitor, and if we take the measurement on the other side of this cap, we can see that we have a DC value added. By design, this should be roughly at 6 volts, because there should be 12 over here, or minus 0.7 volts sitting down there, and this should be in the middle of the two. So this should be around about at 6. Anyways, now let's quickly change these. If we make that 12K and we run the simulation, that is almost half. So the input impedance here is around about 18 kilo ohms. There we go, 18 kilo ohms. Because this resistor here is much smaller than the impedance on this side, that is half voltage. So our input impedance is at 18, and our output impedance should be at roughly 12K. So doof doof, 25 millivolts. That's a quarter of the gain that we designed for. So there's a quick and easy way to check your input and output impedances by playing around with these resistors. So I'm going to make this something a bit more in the ranges, and let's make this 100K. Okay, so you can play around and see the loading effects of your amplifier. Next step, if we want to see all the DC values, right? If we double click here, we can see the DC here on the side, but that is not a good indication. So if we want to remove the AC part, let's just go ahead and delete this line here. We don't need to change anything other than that. This means this AC source is disconnected. So if we run this simulation, we will have our DC values. Okay, so you can click at any point in the simulation. See, this should be close to minus 0.7 volts. This node, it's very close, we can see our DC values. Okay, also, if you click on this side or that side, you shouldn't typically see anything. This is nanovolts. So, in terms of DC, this and that is not visible to our circuit. Right. Another way to see this is if you close this window after you've run the simulation. We maximize this window here. You click on any of these nodes, it will add the DC voltage that you measure at those points. So to get rid of them, you can just go and delete them like all the other entities. And if you run it, everything will be back to normal. Okay, so we connect that again. Circuit is running, amplifier is working, and we can explore even more in this transient analysis. So if we go up here, let's maximize this and right click. We can add cursors. We can add only one cursor to indicate a specific point, or we can add two cursors, multiple points on this. Go ahead there, click OK, and this will bring up the position of your cursors, first and second, and the differential between the two. So you can move them around. To reduce confusion, I'm just going to switch off the grid, and you can move the second cursor. Okay, so here you can do all the measurements and the differences between the two. Finished. And you can add details on your graph. The moment that you close that window, the cursors disappear. Switch on the grid again. Switch to our circuit. Oh, I missed one. And there we go. That is transient analysis in a nutshell. Right, for DC analysis, if you want to see the current that is going through one of these resistors, you can just double click. See, it shows a little circle with an arrow through it. That is to measure current. That is oscilloscope probe. And you can find the current. This is almost at 500 microamps. If you want a better reading, just use one of the cursors, and this is at 514.3 microamps. Also note, if you closed the simulation window, you can get the DC values like I showed you earlier, but not the currents. It can't tag the currents. Next up, our AC analysis. So this is to show our voltage or current versus frequency. It can be used to find the magnitude and phase bode plots of a system, and it shows the frequency response of different nodes in the simulation. So let's jump into that. Alright, for our AC analysis, we are going to use the amplifier that we used in the previous section, and we first need to set up our voltage source here to be an AC supply. Okay, so you right click it, go to advanced, AC amplitude, make that a 1. Okay, if you use 10 milli or 100 milli here, then you have to kind of adjust your bode plot that it provides. This does not take the non-linearities of your circuit into account when working with it. It only uses the model with the capacitors and whatnot. So you can put a 1 here and it will provide you the exact bode plot of your circuit without having to adjust anything. Okay, so AC voltage of 1. Let's make up a simulation, and now we are going to click the AC analysis tab. You want to set this to decade. Okay, so the amount of points per decade, make that 1,000 or 10,000. Start frequency, you can't start from 0, so 0.001, 0.01, 0.11, all of those. So let's have a start frequency of 1 Hertz and a stop frequency of, let's go with 10 meg. Let's see what this amplifier can do. Okay, so the simulation is finished. If we click on this node here, you will find that it is at 0 dBms or 0 decibels, because this, if you convert 1 to decibels, it should be a 0. Okay, if we go to this end of the amplifier, you'll see that we have a lower cutoff and a much higher cutoff that we can't see because this is too low. Double click to take the green away. And here in the middle we have a passband gain. Okay, so our amplifier is designed to give a gain of 10, and that is 20 decibels. Okay, to look at the scale down here, we have 1 Hertz, 10 Hertz, 100 Hertz, 1 kilohertz, 10 kilohertz. So this is every time multiplied by 10. So if this is 10 Hertz, that is 20, 30, 40, 50, and the size decrease up until here where 90 is, and then go to 100. So this is 200, that's 2000, that's 20,000, 200,000, and 2 meg. Right, so let's change this to 100 meg, and we will see more of our plot. Okay. This dotted line here is the phase shift. So if we have a frequency here, there will be a phase shift of 180 degrees all through this middle part. Okay, but as we start to go into this cutoff here, our frequencies start to shift. Also here at the lower end. Okay, so the dotted line is the phase bode plot. Okay, this is the magnitude bode plot. So both is in the same plot for us. So typically this is a good place to play around. If you made sure your amplifier is linear and it's actually operating, you can start to play around with components. If we make this 120 ohms, our gain should increase. Okay, and it's increased by quite a lot. So every time we reduce this, our gain will increase and it will show. Also, playing around with the capacitors, if you make this 10 microfarads, make that 10 microfarads, these two are both low frequency capacitors, so it will have an influence on this high pass effect. We run it, you can see that this has moved more to the left. Okay, so increasing the cap sizes makes this cutoff frequency at a lower frequency. So let's reduce these to 100 nanos, and you will see that this absolutely shifted to the right hand side. Okay, so you can play around with your capacitors to kind of fix your lower cutoff frequency, like that. Quite easy. And also change this resistor here and see your gain immediately in a boat platform. So running this should be at a gain of 100. And so you can refit your amplifier to fix any problem that you see, fix your gain, fix the phase if necessary by adding the capacitors, adding more capacitors. If we add one here in parallel with the load, quickly do that, we can change our higher cutoff frequency. So let's make this 10 nanos. This impedance that I'm using here is quite high, so let's rather reduce that to 12k. Our gain will half, and we will see a change in this higher cutoff right here. Run it, and it's been decreased by a lot. Since we only halved our gain by adding that 12k there, we only lost about 3 dBs. dBs is the half point, so we didn't lose that much. So increasing this, we will decrease our frequency even more. And by decreasing this, let's go over 100 pico. There we go. Okay, so every time we up this, we will decrease our higher frequency. There we go. And you'll see that this also has an influence on your passband gain. Let's see what the effect is by choosing a different transistor. So let's search a nice high frequency transistor. Let's go with this quad 2. Not much change in the frequency, but we did have a change in the phase. Okay, so picking different transistors could have a big influence on your amplifier itself. In this case, we will not be seeing much because we added a high frequency cap there. Let's see, this goes way beyond. So let's make this 1 gigahertz. Great. Let's change this again. Pick transistor. Let's go back to the quad 2. And you see that there is a slight of a difference in the high frequency cutoff there. Let's choose one by random. Let's see, let's go with that one. Oh, boom. See, it's got a lower FT value, transition frequency, and that reduced our bandwidth by quite a lot. So you can also study the effects of using different transistors in this. But look, our gains stayed kind of stable and our lower cutoffs stayed fairly stable. So our transistor choice only affected our higher cutoff. And yes, we can also again use our cursors, and we can use our cursors to find our -3 decibel point. So for the first cursor, we want to go to a gain of 31.7, so around about there. And our second cursor also to 31.7. So if we align these two, there is our two cutoff frequencies at 40.6 Hz and 57.74 kilohertz. So if we change this back to our BC547, this will increase. Let's see, our midband gain is still at 43.7. 54.7, so let's take this again to 51.7, and our second cursor 31.7. So our lower cutoff now is 25.6, and our higher cutoff is at 15.7 megahertz. Okay, and that is all that you need to know about the AC analysis. So select AC voltage of 1, you can use cursors and you can have a nice boat plot, play around with the values, and you can see the effect immediately. Also, if you're designing a circuit and you're testing it with 1 kilohertz constantly and you're not seeing the results, right? But there is an output, but it's not exactly what you wanted. Quickly pop over to AC analysis and see the baud plot. Sometimes the frequency that you are using as input is on one of the cutoffs, and you should just readjust for that. Okay, that is the AC analysis complete. So for our next AC problem, I went ahead and set up our op amp. Okay, 1 kilo in the input, 100 kilo in the feedback, so this thing should have a gain of 40 decibels or a gain of 100. I set up two simulations. You can also set these up using the spice command, so just dot and whatever, and you can just paste it on the schematic, and it will ask you to select one of the two when you start and try to run a simulation. Okay, so I set it up to do a transient of 10 milli and AC for 1 hertz to 100 megahertz. Okay, the op amp that I used from the library, I used Universal Op Amp 2. So this is a perfect op amp in inverted commas, but it still shows gain bandwidth product. Okay, so let's jump into this. So let's run, and let's first select that we want to do the AC simulation. Runs the AC simulation, and if we click here, we see our gain of 40 decibels, and then at a higher frequency we start to see a drop. Okay, so if we reduce this to 10 Ks, our gain would go down, but our bandwidth would increase about 10 times. And if gain of 10 and a bandwidth increase. Okay, so you can use this to also observe the gain bandwidth product issues. Next, our DC sweep can be used to find the transfer function of a system. So it shows us the input versus output plots. It is useful to find bias points. So if you need to insert a specific DC offset into a system with your signal, you can find that point. It is also used to find the input and output limitations of a system. It can also show you non-linear regions in a system. And lastly, you can use it to find transfer functions of different components. So let's jump into that. For our DC offset, I have set up two op amps, non-ideal op amps from the library, and I've set them up both to have a gain of 100, and I went ahead and I set up a transient analysis for 10 milliseconds. Well, visible at 10 milliseconds and input of 10 millivolts. So the output of each of these should be 1 volt if we run a simulation. So let's run a simulation and let's check the outputs. So this one has output of 1 volt peak, but it is offset, and this one also has output of 1 volt peak, but there is no offset. Okay, so one thing to remember is to always compensate for the offsets or to check for it. So let's quickly compensate this first one. For the DC analysis, the DC sweep, and I'm going to show you a problem that we are going to encounter. This one should now be fully compensated. Okay, so they line up and there's a slight phase difference, but that is due to the capacitor. Okay, so the purpose of a DC sweep again is to find the transfer function of one of these amplifiers. So let's go ahead and do that. If we right click this, we can say we want to do a DC sweep. Number of a source that we want to sweep is this V3. We want a linear sweep. I want to sweep from -11, so value less less than our lowest and higher than our highest value, so from -11 to 11, and let's do it the increments of 10 millivolts. Click OK. Let's close this, run the simulation, and you see here at the bottom we have from -11 to 11. If we check this source, you will see that it increases from -11 to 11, and I'm comparing the source to itself at this point. So if I go and double click here, you can see that from -11, this is as an inverted output, you will have a output of 8 volts. So -11 will provide 8 volts up to this point, and then there's a discontinuity and down to 11 volts. Okay, so The 8 volts that we're seeing here and the minus 8 volts that we are seeing here is the saturation of this op amp. Okay, so this axis is the output and the bottom axis is the input. If we zoom in on this center section here, you'll see that there is a bit of a non-linearity, then it's linear and non-linear again. This line here is the gain. This is the output saturation, and then these 2 points here would be your input limits. So let's place 2 cursors. One we take to that point and the second one we take to this point. And we'll find that we have an input differential of 161 millivolts, and the slope that we are measuring is minus 99.35, which is close to minus 100, which we should be seeing. Okay, so this provided us with all the limitations of this amplifier, and it gives us the transfer function. Right, zoom to fit. If we check out the second amplifier, we don't get anything out. This is because we inserted a capacitor here to deal with our offsets. Okay, and this capacitor is a DC blocking capacitor. So to simulate this, you're going to have to go and remove this capacitor and some of the other effects might creep in if you do this. So if we run it now, we can see our amplifier's output, and we can see the gain and the input limitations to this op amp now. Right, so we can compare the two amplifiers. Clearly the one has offset and the other has a rail-to-rail output. Okay, so but we do remove offset if we include the capacitor. And that concludes our analysis of these two amplifiers. So DC analysis provides us with the input versus output. Lastly, for the DC sweep, I set up a voltage source and a diode. I didn't include a series resistor here because I want to see the voltage versus current. So we are going to change the voltage across and measure the current through this diode. Okay, so to start a DC sweep, we want to sweep voltage 1. The type of sweep is linear. Started from 0 volts, end value 1.5 volts, increments 10 millivolts. Right. The simulator does not take into account where this diode breaks. Okay, so you right click on this, you will see that it breaks down at 75 volts backwards, and forwards you will also find that it breaks down really soon. So you can go and look in the model or in the SPICE model of a data sheet where this diode breaks. You will not break it in the simulation. Okay, so always be mindful that it's going to simulate perfectly no matter how you increase that voltage, it will still work. Okay, so this voltage is from 0 to 1.5 volts, and if we have a look at the current here, closer to 0.66, it starts to switch on and it increases up until here at 1.05 amps. You can see the non-linear curve here. Let's pick a different diode, run it. You will see that it actually switches on a bit earlier. Let's find a different diode type. Let's go with Schottky here, run it, and it switches on much sooner, closer to 0.3 volts. Okay, so you can go through all the diodes. Let's go with Zener, run it, and the Zener switches on at 0.4. If you want to see the Zener effect, we're gonna have to rotate this component, and this is a 6.2 volt Zener. We are probably gonna have to increase this stop value. Let's go to 10. Run, and here at 6.2 volts, it switches on. Okay, and there you can check your components when you are working with them. Find the transfer functions of them. If you want to do this in a normal way, if you reverse this voltage, it will still act as a normal diode. So for the Zener, since it is important for the directions, we can probably find the whole transfer curve. So yeah, switching on at 6.2 and beside normal diode functionality. And that is it for the DC sweeps. Lastly, our fast Fourier transform, or our FFT. This we use to analyze harmonics in a system. So if you drive a system into its non-linear region, some harmonics will start to exist. So you can use the FFT to visualize our harmonics that's generated, and you can use that to perform a total harmonic distortion analysis. So let's jump into those simulations. For our FFT, we are going to use the same circuit that we used in the transient analysis, and we are going to start off by doing a transient analysis, which I've already done. And you can see that this sinusoid is to the eye quite pure, okay? And this input signal is kind of still small, so our circuit is acting in a linear fashion. Okay, so if we select this right here and we go to view, we can say plot a FFT. Okay, we select our node that we're plotting, and this is the output node VN2, VN2, VN2. So you can find whichever node is in here and select it and click OK. So at 1 kilohertz, you will see a peak, and this peak is at almost minus 20 decibels. Okay, 100 milli, if you put it into a log, it would be almost minus 20 dBs. So here you can also add cursors to do your measurements. Switch off this grid again. You can see what we're doing. And there we go. So that is our fundamental harmonic at 1 kilohertz, the one that we input. Right, so we can see that this is sitting at minus 24 decibels. We can move this to this point. That's 2 kilohertz. That is, if we should see a second harmonic popping up there when it's not linear. And there is going to be other frequency components, but this is mostly noise. Okay, so if we change anything in our simulation, we need to rerun the FFT every time. So I'm going to close this window. Okay, let's first make this 100 meg. Okay, to have minimum losses, and let's make this 1 again and run. Our output is now at, we should see exactly 100 millivolts, and this is still at 10. So if we do a FFT on this, we should see that this is now approaching more to the minus 20 dB area in any case. Okay, so that is the actual size of the sinusoid. All these other components contribute to this data, and remember that this data is also digital data. So some of this noise is a contribution of this signal not having enough points being used. So the amount of data increase, this figure will become much smoother. Okay, so this FFT is more of a rough idea. Right, now if we increase this input signal, this still seems fairly like a sinusoidal wave, and at some point it's going to start to become very non-linear. So let's insert 1 volt. Oh, that's driven it into saturation. Okay, so basically if we look here, it is up to 12 volts and this is down to 0 volts. So inserting 1 volt multiplying by 10, we can't really reach. Okay, so for interest's sake, let's do a FFT on this. Need to select the window. Let's do FFT, run it, and you can see that, okay, this is now above the 0 dB line. The signal is much larger, but it's not a 10 volt signal, so this is smaller, but you can see harmonics that's popping up here. Okay, if you look at the block wave, this is the typical kind of signal that you should be seeing. Okay, so these points can be used in a total harmonic distortion analysis, and this signal is very distorted, so the percentage for the THD would be very high. Okay, so you can see that there is extra peaks that is kind of dominant, almost 1 volt here, almost 1 volt, much less going on. Okay, so let's decrease this input signal a bit. So let's go with 500 milli. That should be doable. We run it, we can see that we have the sinusoid But if we look at the edges, it's not really that pure anymore. Okay, so if we do a FFT, you will see that some of our harmonics will be a bit more dominant than in the first case. So here is a prominent first harmonic. It's not saturated yet, but this is almost in the range of our first 100 millivolt signal that we had, and this one is a bit larger. So you can see that there is an extra frequency term being added to this. And if you put this near a pure sinusoid, you will actually see the difference between the two. And you see that this is more sharp at the edges, and this one is a bit more rounded. Okay, so it is distorted. It's not that clear to the eye, but if you do the A50, you can see the difference. Okay, and that is the A50. I will revisit the A50 when we are looking at a oscillator example in a later video, but this will give you an idea of the non-linear effects of a BJT and what's happening if you drive this input to be much larger than 10 millivolts at VBE. We can drive this one quite high because we have a very large input impedance and a quite nice drop across this emitter resistance here. Right, so if we go and decrease this resistor here, let's say to 120, the gain of this amplifier should increase, right? There we go. And let's decrease the signal to 10 millivolts. We can see that we have a gain of about 70 with this resistor decrease. This also means that this impedance here have decreased and we can drive our amplifier into a non-linear region much easier. Okay, so let's go 50 there. Still not. It is a bit more lumped. Let's go 100, but I think that's gonna drive it into saturation. Yeah, at the bottom it drove it into saturation, but at the top you can see that it is very round. It is not as sharp anymore. Okay, so this is a very good example of this transistor not being in the linear region anymore, or not being used as a linear amplifier anymore. And people tend to forget that this input signal here is much very related to that. In the previous one, we could up this signal because we had a larger resistor down here. Okay, so let's quickly check the effect in the A50 for this one. Run it and look at that. These large harmonics that's being generated. And this is also due to the saturation at the bottom, and the top over here is a bit more, well, for lack of a better word, fat, not sinusoidal anymore. And you can see these effects in the A50. So if we run a A50, let's say on the input signal here, run A50, you will see that these harmonics are much smaller, and this input being 100 millivolts, and there we go. Okay, and that is all for now for FFTs, and I will see you in the next video for importing models. into LTSpice. Thank you for watching and see you later.